Okay, so empirical formula is just going to be a formula that shows symbols for the elements in a compound with the subscript showing the smallest whole number ratio. So that is the big key point here, is that is the smallest whole number mole ratio. Now, when we say mole ratio, that's something that we are going to really do a lot more in stoichiometry when we're dealing with coefficients. But for this one, the mole ratio, it can also be known as your subscript. So we're talking about the subscripts. All right. So when we have a chemical formula such as H2O, the little 2, it's sorry, let me write that out. There you go. A little 2 to a 1, that is a 2 to 1 mole ratio between hydrogen and oxygen. Okay, so that's what we're talking about here. So usually for our ionic compounds, we've already reduced them down. So you don't see Ca2O2, right? So we've already established that, since that happens to be a crystal lattice where these things are kind of repeated over and over and over, this mole ratio we keep reduced to a 1-to-1 ratio, right? When we crisscross the charges, okay? And then for molecular compounds, that's when things aren't necessarily reduced down automatically, right? So we've seen stuff where we could have hydrogen peroxide, which is H2O2, right? And we wouldn't reduce that down because that is different from something like H2O. Like we want to establish, and that's even, it's something else that's different from if we had OH or HO, right? So, so molecular compounds are not those guarantees. And that's why we have this thing called empirical formulas. So when you're given a molecular formula, that's known as your true formula. But we have this little simplified or summarized version of it, which is the empirical formula. So the example that you see here, B2H6, can be reduced to an empirical formula of BH3. Now, could the empirical formula and the molecular formula both be BH3? And the answer is yes. So sometimes your molecular is equal to your empirical formula. But something like this would be considered the molecular formula, and this would be considered the empirical formula, right? And so just know that they can be the same. So your molecular can be your empirical, but your empirical does not necessarily mean it's your molecular. Okay. All right. So what you're going to see in this little assignment is you do need to be able to take a molecular formula and reduce it down to empirical formulas. And you'll probably see that more tomorrow. So for today, our goal is, how are we going to get this empirical formula when we're dealing with percent compositions, which is what we've dealt with in the previous lesson, where we had part over whole times 100, and that gave us a percent of each piece, right? So I could get my percent of hydrogen, or I could get my percent of oxygen. So how do I take those percents, if that's what I'm given? Because we can do percent by mass in the lab. How do we take those percents and now find this empirical formula? Which then tomorrow you guys will learn that we can take that empirical formula and we can then turn it into a molecular formula. So it's all connected. So today our goal is just empirical formula. All right, so let's get started. So when we're finding empirical formula from a percent, all right, you have 4 main steps. And so we'll go ahead and start. I'll kind of color code these so that you can see the steps actually happen in the example itself. So the first thing is that we're going to assume a 100-gram sample, okay? And so what I mean by that is it's a really tricky step. And what that is that when you're given these percents, right, they're given to you in the problem, just like this, 32.38% sodium, okay, we're going to take that percent, we're going to scribble it out, and we're going to replace it with a G. That's the fancy step. And the reason I said that we are assuming a 100-gram sample is that, well, if these percents were all describing percentages in a 100-gram sample, then this is not 32%. It's going to be 32 grams, 22 grams, 44 grams. So that's all that part means. Okay, so the next thing that we would do is we would convert our grams to moles. Okay, and so what we've seen previously in our dimensional analysis practice that we did, when we had grams right here in our little T-chart, we would bring the words down to the right. So grams would come down to the right, and we would put moles on top, right, if we were converting to moles. And this would end up being this step right here would end up being a molar mass to 1 mole thing. So what this really means that we can do is we can just take it and we can take our 100-gram sample grams amount and we can just divide it by the molar mass found on the periodic table. Okay, so once we have things now all converted into moles, the next step that we can do is we are going to divide all the moles by the smallest. And what that's going to do for us is it's going to give us a guaranteed 1, right? So if we divide them all by the smallest, then that value divided by itself is the number 1. And therefore, we're now creating a ratio with these subscripts, okay? So we're going to divide all of those things by the smallest. Finally, our last step is those numbers, those answers, become the subscripts. And every once in a while, they'll have one additional step, okay? So rounding is going to have to occur in this step, except when it's a 0.5 ratio. When we're at 0.5, we're going to have to do an extra step, and we'll just worry about that when we get to that in the example. All right, so this first one does not have that extra step, so we're just going to be sticking with numbers are going to be the subscripts. Okay, so looking at our values that we have over here, I'm just going to rewrite them real quick, give us a little bit of space of sodium. And then we had 22.65% of sulfur. And then we had 44.99% oxygen. All right, so that first step says we're going to assume a 100-gram sample. So we're going to do that fancy step where we're going to cross this out. We're going to replace it with a grams. We're going to cross this out. We're going to replace that one with grams. We're going to cross this out, replace that one with grams. So we did step 1. Our next step is we're going to be converting things to moles. So I'll show it with this oxygen down here because I have the most space down here. But if we have grams of oxygen right there, remember we brought grams down to the right. So grams of oxygen, we're trying to convert it into moles. Okay, so this ends up being the molar mass. So if I were to pull up my little periodic table, we see that oxygen is 15.999. So we would put the molar mass down here. So I'll just go ahead and label that so that we know what we're talking about. 15.999 grams per 1 mole. So this ends up being a division problem, right? 44.99 divided by 15.999. So when we get that, we'll go ahead and handle our calculator for this one. Divided by 15.999, we end up with 2.812. So we'll go to 4 significant figures. And we're going to label it moles. That's our answer, right? Okay, so for the rest of these, I'll kind of do the shortcut, which is just divide by that molar mass found on the periodic table. So for this one, we have 22.65 grams of sulfur. We're going to divide that by the molar mass of sulfur, which is 32.066. So again, I'm just saving some room here. So this is the molar mass. We're still dividing by that molar mass, okay? So when we divide that value, we get 22.65 divided by 32.066. We're going to go to 4 significant figures again. So here I see 0.70635. So we're going to go up to 4. So 0.7064. And then finally, we're going to divide our sodium amount by the sodium molar mass, 22.990. So when we type that one in, we get 32.38 divided by 22.990. Should have said 0 right there. And when we do that, we end up with 1.408. Okay, so we just finished step 2. Now we're on step 3. We have to look at these 3 values and we have to decide, okay, which one is the smallest? So looking at these 3 values, you do see that this is the smallest value. So we're going to take all of them and we're going to divide it by that smallest value. So 1.408 divided by 0.7064. We end up with 1.993. Okay, this one we're going to divide it by itself. So that one I'm not going to type into the calculator because anything divided by itself is equal to the number 1. And then this one we're going to divide it by that smallest, which is 0.7064. Let's go ahead and type that one in. And then I'm going to make a side note here in a second. 2.812 divided by 0.7064. So we end up with 3.981. Okay, so looking at these values, our next step is we need to round them to a whole number, right? So, and those things are going to be our actual subscripts. So we'll go ahead and round these all. So this is approximately 2, right? It's really close to 2. This one is 1, and then this is approximately 4. So now we're going to take those whole numbers and we're going to go ahead and put them as our subscripts. So the reason that we're doing this, the whole reason that I even added this rounding part in is because we don't write our formulas. You haven't seen anything so far this year with decimals, right? So we don't put NA 1.993, S, and then O 3.981, right? Like that's just strange. So that's why we're rounding these to whole numbers, because looking at these, we're dealing with mole ratios. Mole ratios is a whole number relationship here. So it's Na2SO4. And that's actually the final empirical formula. Now, I do want to make one more side note. Some of us can look at a decimal like this and say, okay, 1.4 divided by 0.7, and you possibly were approximating in your head approximately 2, right? And then this one was 1, and then 28 or 2.8 divided by 0.7, you might have already been coming up with 4. That is okay. On this step, when you are dividing by the smallest number, it is okay to approximate if you're able to do that part in your head. The only part that you would run into an issue is if one of these came out to be 1.5 or 2.5. If we see something ending in 0.5, again, not in this step, but in the green step over here, if we got something that was 1.5, we would have to then go back to each of these and multiply it by 2 to get rid of that thing. So that is the only one that you are not allowed to round and you are not allowed to approximate. Okay, everything else is fair game. Okay, so I just want to make sure you guys knew that part. So moving on, our next example is a little different. Okay, so this next one, we're still going to approach it the same exact way though. Okay, I'm still going to bring us back to a percent and then we're going to go through the steps. Because I want us to master this, all right? Is there a quicker way? Yes, and I will go over it at the very, very end, okay? But for now, what we have is we have a 10.150 gram sample, so an unknown sample. But it has phosphorus and it has oxygen. And then it tells you that, okay, well, phosphorus is this much, so what is the oxygen? So you have 2 options, and I'm going to go the percent route, okay? So some of you guys might look at this and say, well, we could skip that. That's true. All right. But for now, I want us to go back to percent composition. So remember, percent composition was part over whole times 100, right? So we could say 4.433 divided by our whole, which is the 10.150. And that would get us 4.433 divided by 10.150. We would get 0.4367. So then we would multiply that by 100 to get 43.67% phosphorus, right? So I'm trying to make it look exactly the same that we started over here. Okay, So if they don't give you the other information, what can we do here? You have two options. You can either solve for it by taking our 10.150 minus the 4.433, because whatever's left over is the oxygen. Or we could take 100 and we can subtract this 43.67. So you have different options there too. We're going to go ahead and go the 100 route. So if I have 100 minus 43.67, we get 56.33% oxygen. Okay, so now we're going to start here, okay? So once again, I'm going to change my colors here. We're going to assume a 100-gram sample instead, right? So we're going to change those to grams. Then I'm going to go ahead and divide it by the molar masses of each in order to convert things to moles. So bringing up my periodic table, there it is. Okay, so phosphorus is 30.974. So we're going to divide this 30.974. So 43. Divided by 30.974 gives me 1.4098, which we would round up to be 1.410 moles. We would do the same here. So we have oxygen, we know is the 15.999. So we would end up with 56.33 divided by 15.999. We would have our 3.521. Okay, so now that we have our moles, we're in the last step, not last step yet, third step, we're going to divide all of these by the smallest. So looking here, I have 1.41 moles or 3.5 moles. So we're going to divide it by this 1.410 so that we can have one of them come out to be 1. So this divide by itself would be 1. This one over here, we end up seeing that 3.521 divided by you can see the answer way up here. So it says 2.5. All right. So this is one of those examples where we're going to end up with that 0.5, like I've told you right here, right? So remember, we're not doing it in the blue step. We're doing it right here in the green step, right? So once we're here, we can't just round these both up, right? We can't just round everything. So once we see this is that additional step that we have to do. So we have to get this to a whole number. So the best way to get this to a whole number, right? So if I have 0.5, the best way to get that to a whole number is to multiply it by 2, right? And that's the concept that we're going to be using here. So we would round this, or we would multiply this by 2. Whatever we do to this one, though, we have to do to the others, okay? So now we're left with a 2, and this one would be a 5. So the answer for this empirical formula would be P2O5. So diphosphorus pentoxide.